Hello and welcome back. Today we are going to continue our discussion on convolutional neural networks, but we are going to take a slightly different approach. We are going to identify why these work, which we have already discussed, uh, but how can we really build neural networks that generalize, and what are the hyperparameters in a convolutional neural network? So, if you think about a convolutional neural networks, it's a more efficient way of learning from a limited set of data in comparison to fully connected neural networks because they share weights and those weights of the filter are localized to a given region within an input image, and then they're able to learn hierarchical representations. They also have invariances in terms of convolution built into them, and those are really helpful when you have an image classification task. However, I think I should also emphasize that image classification is not the only place where you can use convolution or convolutional neural networks. You can use them on signals as well. Even if you have three-dimensional MRI data, you can use that. You can use three-dimensional convolutional neural networks and so on. So there are other variants as well. But for the sake of our discussion and without any loss in generalization of your learning, we can restrict our discussion to image-based classifiers using convolutional neural networks. So the given task is, of course, image classification. You're given an input image with a corresponding label, and we want to use a neural network for that. Because of these desired properties or these really good properties of convolutional neural networks in terms of locality of learning, shared weights, these are actually much better representations of, they can offer much better generalization in comparison to fully connected neural networks. We are going to take a look at what are the hyperparameters of these machine learning models or these convolutional neural networks. Remember, hyperparameters are parameters like kernel, what kernel we use in support vector machines, or what are the kernel parameters, and so on, right? And the way we selected our hyperparameters there was to use a validation data set. Here, first we are going to try to understand what is the impact of different number of hyperparameters. There are much larger number of hyperparameters, and that's why it's really important to understand the role of each one of them and then try to use them in and to keep that in your mind when you are trying to use them in practice. So just like a regular neural network, which has how many uh, like how many neurons or how many layers you want to have of neurons, what is the number of neurons within each layer, what is the activation function that you want to use within each layer or for each neuron. All of these have an impact on the prediction performance of your neural network. That all also holds over here. So everything that we talked about of how we can improve the prediction performance or generalization performance of multi-layer perceptrons, it also applies over here. Let's say if you've got we can analyze the prediction performance or generalization performance using these convergence plots. So if you are trying to train a neural network for a given task, it's always important that you try to analyze its prediction performance on using these convergence plots, using both a training data set so that you can analyze whether the neural network is converging or not, and also using a held out validation data set that gives you what sort of performance can you expect in the real application of this problem to a practical setting or at test time. And it also gives you an idea if your neural network is overlearning or trying to memorize things, so you can implement something called early stopping, so that you can stop your neural network training at a point where your validation error is not too large, so you don't have memorization. And that's how we can train neural networks. So everything we've discussed earlier for multi-layer perceptrons also holds here. But specific to convolutional neural networks, the parameters or the hyperparameters you have is how many filters should I take? What should be my filter shape? Should be my kernel size? Should it be 5 by 5, 3 by 3? Which is also called the receptive field, because that is the part of the image on which at a given time your neural network is focusing on. So that's that bit. What should be the pooling type that I should use? Should I use max pooling? Should I use average pooling? What should of regularization should I use? We haven't talked about regularization in terms of convolutional neural networks or networks or neural networks in general, but regularization, the idea of regularization is also present within neural networks. And we're going to talk about that and how can we essentially how can we optimize uh, or expect to optimize the generalization performance of our neural networks. Now, it's really intuitive if you start thinking about it. Once we develop a neural network, the supervisory signal we have is the label or the prediction label for a given input example. We compare it to a target, we feed that error back into the neural network. Now, if the object is difficult to identify, then having a sufficient number of filters is going to be really helpful. If you don't use enough filters, you'll not be able to do well or in detecting or classifying that object. So without giving you any number of how many filters you should use, because that is also dependent upon how many layers you have. So all of these are like affect each other, all of these hyperparameters. You should have enough number of filters to capture the variability of different object representations within your image. And that can vary from problem to problem. If your objects are like always like this, have a very fixed pattern, probably you don't need a very large number of filters. Or you may not even need a very large, you may not need even a very large number of convolution blocks. And you could still be able to produce very good performance on the test set. Remember, that is the only performance that really matters. So you can relate that over here. If the object is very of a certain morphology all the time, you do not need a very large number of filters. But if it has certain diversity, for example, imagine a bird flying, it can have different modes. And if you're trying to identify different types of birds within a given input image, that's a much harder task than trying to simply predict whether there's a bird or not. So you can have the number of filters is actually dependent upon that. The size of the filter it also depends upon two things: how many objects, how many layers, sorry, of convolution blocks you have in your input, and how many, what is the size of that object. Remember, once you have a convolution neural network, you're trying to pass the output of a single neural network, the convolution layer of that neural network into the next layer, which passes it on into the next layer, and there is pooling taking place, right? So we have information compression due to that pooling as well that we should take into consideration when we are trying to decide filter size. There again, there is no single answer. We need to find that out using our input, our convergence plot. So let's say if you're trying to detect objects or classify objects that are large, then you may want to have either a very large neural network or you may want to have a high information compression taking place in the initial layers of your neural network, so you can have larger filter sizes. But that comes at a cost, because when you use a large filter, you end up with a very large number of parameters, and then that can inhibit your learning. So it's essentially a compromise between depth, between the size of the object that we are interested in, how many morphologies, what are the scales of that object that object occurs in. So it's again, there is no single answer over here, and the only way we can identify that is to use these convergence plots. And if you have an intuition for that, we can definitely use that as a starting point and then try to improve upon that. Similarly, pooling type and shape also is a factor. How much information reduction needs to be done? You can have max pooling, you can have average pooling, you can have different shapes of the pooling size, you can have different strides, but all of that is again dependent upon the input image and the type of problem that you are trying to solve. So all of these hyperparameters, how many filters should I use, what type of pooling should I use, that is all dependent upon the type of problem you are trying to solve. Typically, I encourage students to start off with pre-trained neural networks for generic image classification tasks such as ImageNet or CFAR10 or MNIST dataset. So you can start off with very simple neural networks that have already been pre-trained on these neural networks, and then you can use those neural networks in something called transfer learning for your own problem. And the way that works, without going into too much detail at this time, we're going to cover that in a bit anyways. Let's say if you got an input image, if you got a task, and you already have a neural network that has been pre-trained on, let's say, ImageNet for classification, then the way it works is, or the way transfer learning works, is you use that neural network and you only train the classifier or retrain the classifier portion of that on your task. So you can use transfer learning as a starting point. You can identify it as a baseline, and then you can go into implementing different type of priors or different types of domain specific filters or you can choose that number of filters, you can vary that, and you can improve upon that classifier baseline by playing with different number of filters with different shapes and so on. Okay, so that's one thing. In terms of the concepts that we discussed earlier in our machine learning models, we had a concept of structural risk minimization. We should be trying to minimize the empirical error as well as introducing regularization. The same thing holds for any type of neural network as well. We can do regularization within the neural network, and that is going to help us maximize the generalization performance by limiting memorization within the neural network, right? So that a small change in the input doesn't produce a large difference in the output of the neural network. The same concept applies over here as well. However, the methods that we can use to implement regularization are different. We can use something called dropout. We can use data augmentation. I'm going to talk about all of these. We can use early stopping as a form of regularization. So you can have norm constraints, you can have L1, L2 regularization within your neural network as a means of achieving an effect of regularization. Remember, regularization is simply that a neural network or any machine learning model should not change its output when the input is changed by a small amount. That allows us to minimize overlearning or memorization that we've seen in support vector machines, for example. So if you choose a very complex kernel of support vector machines, you may overlearn, but if you use a much simpler kernel, you may not be able to learn the concept that you're trying to learn, and you're essentially using regularization as a means of achieving good generalization performance without overly complexing, or I just made a word up, making your classifier overly complicated. Okay, so that's the goal of regularization. As we discussed earlier, one of the very simple ways you can implement regularization is using early stopping, and that's what we're going to start off with. Then we're going to talk about data augmentation and so on. But let's first talk about the optimization bit. So the way neural network training works is that you, for a given number of n epochs, you pick a batch of examples using a data loader, you pass them through the neural network, you compute your loss because you know the labels, and you backpropagate, and then you can keep doing it for a number of epochs and then you stop. However, the problem with this is that you will never know whether the neural network has achieved maturity or has been able to learn the problem or solve the problem that was given to you. And so if you just plot, for example, the loss of a given neural network across epochs, you can see a curve like this, that your your training error or training loss goes down. Now that's good, and we should see that. What that indicates is that your neural network has been able to optimize, or it has been able to achieve convergence. So this plot is useful, but we don't know whether it has overdone it. That is, if it has learned, started to memorize those examples rather than trying to generalize. So what we do then is, within each training epoch, we compute the error over a validation dataset that we have held out, and we plot its error across epochs as well. And we have training, if you plot the validation error, if you plot epochs on one axis and this training error on the other axis, we can do it after each epoch. We measure how much training error we have and what is the corresponding validation error. And as long as our validation error is decreasing, we are good. But once it starts increasing again, we may want to stop the training. Another way of implementing the same thing, called early stopping, is we keep copies of our neural network or the parameters of our neural network after each epoch. And once we are done with training, we pick the point where the neural network was giving the lowest error on the validation dataset, because that is the point where the neural network started to overlearn. Okay. So this way of selecting a optimization problem, solving this optimization problem is called early stopping. We are essentially trying to stop learning where the neural network starts to memorize data rather than generalize it. Okay, and this is a way of learning, or it can be thought of as to have a regularization effect, in that your neural network will now produce more regularized outputs. A small change in the input or a small difference in the training and the test set is not going to produce a large difference in the prediction performance of your neural network. So it has a regularization effect, although a very indirect one. And that is why we started off with these simple machine learning models where you had precise control over regularization. Here, there are multiple different factors like early stopping, your gradient descent method, even the parameters of that gradient descent method also factor into this regularization effect. So it gets a bit more complicated. But you can always, and I repeat, always plot the loss over training and validation data across epochs, and it gives you an idea of whether your neural network is converging or whether your optimization is successful, and which is always a necessary requirement for learning to take place. But also we want to verify whether learning is indeed taking place by plotting our loss on the validation dataset, so that we can expect that a neural network would now generalize to a given test set. Okay, so this is really important, and it is a way of ensuring regularization within your neural network as well. The next way, or another easy way of doing regularization, is to do something called data augmentation. So let's say you've got a bunch of input examples. If that number of input examples is small, let's say if you only have 1,000 input examples, you may want to increase that number artificially by adding some noise to your input examples to create new variants, or you can have rotations of your input images if your input task is rotation invariant, so that your neural network is able to learn in a more effective manner, and it's able to learn those patterns that are not that don't lead to a difference in your classification output. For example, if you want to detect Waldo, where Waldo is matters if you're trying to do a detection task. But if you're doing a classification task of the form, does this image contain Waldo or not, we can generate artificial data from a given example by moving Waldo around across the images, and then we can have more examples. But essentially, this is a way of forcing the neural network to learn that the task that we're trying to solve over here is invariant with respect to the location of the object. So that's what we can achieve with this. There are different type of data augmentations that you can use. For example, for a given input image, if you have a label like this, a bear reading a book, you can flip it, so a horizontal flip, because that is not going to affect the label. So you can do rotations, you can do random crops. Let's say if your object, if you're interested only in classifying whether there is a bear in this image or not, this random crop should not affect the output of your output label. Similarly, doing color shifts within reasonable amounts can also be used as data augmentation. You may want to add some noise to make it robust to noise. Sometimes you may even want to add to remove certain sections out, like this one, so that it doesn't fixate on any specific patterns that are only specific to a certain number of images. You can also increase or decrease the contrast. There are so many other things or so many other games you can play to do data augmentation, but the main goal is to use a small data set to be able to generalize better over unseen cases by making the neural network invariant to all of the things that don't affect our prediction label. That is a way of regularizing, so that a small change in the input, for example, by a small change, by introducing a small amount of noise, the label should not change. That is how regularization is achieved using data augmentation. So we talked about this one, we talked about this one. You can also use, notice your neural networks and your filters are essentially nothing but more than those weight values, and you can penalize those weights much like you had in a support vector machine. You can reduce the norm of those weights by specifying a penalty that is associated with those weights. So you can have norm constraints, or you can have L1, L2 regularization. All Python packages or all machine learning packages for neural network training actually have these all different type of regularizations built in. You can have early stopping, you can do norm constraints, you can have L1, L2 constraints, you can even do different type of data augmentations. Those are supported by these packages in Python, so you can go ahead and use that. We are going to discuss these regularization mechanisms in a bit more detail. Let's say you've got a neural network which has a certain number of weights or weight parameters. You can choose a penalty to force that those weights are not too large. Remember, whenever the weights get large, if you follow up our discussion on multilayer perceptrons, then some of those, the output for a given input can be very large, and that can reduce to vanishing gradient problems. and that can inhibit your learning, right? So it's always a good idea to regularize your weights within the neural network by specifying a regularization parameter to your cost function. So instead of just minimizing the loss that is overtraining data, so you have for a given set of examples, if you say that you've got a neural network with weights W, and the output for a given example is f of xi, you have the corresponding target label, which is yi. So you can simply do a loss term over here, or the empirical, or then you can use an empirical loss in your optimization parameter, which can be, let's say in this case, it's a sum of square error loss for a given input example, a set of given input examples. But you can also add a regularization term to inhibit the growth of large weight values. So this is called a weight decay parameter that is available within PyTorch. And what it does is essentially adds this L2 penalty to your learning so that you don't end up with weights that are very large, much like what we, or you run into overfitting problem, much like you had it, the same thing in support vector machines. So this can be used to handle problems such as generalization, and this is a way of achieving regularization as well. Please look into this weight decay parameter in PyTorch help to understand it a bit better. There are other ways you can also handle or you can implement regularization. One of them is to clip the gradients of the neural network. So if your neural network, once you compute the errors, you compute the loss of your training examples, you take the derivative of that loss. If that derivative is pretty large, you may want to reduce that effect. You can simply do a clipping of the loss gradients with respect to a certain weight, so that once you add or you update your weights, your new weights are not too large. You can also reduce the learning rate to achieve a similar effect. So this learning rate parameter also has a regularization effect, but it can slow down your learning. Okay, so this is another way. There is another way of you can handle these vanishing gradients or exploding gradient problems, and that is using what is called pre-training. I'm not going to go through this in detail, but you're welcome to explore it on your own. The two things that I want to talk about of achieving regularization, one of them is called dropout, and the other is called batch normalization. For understanding the first bit, let's say we've got a fully connected neural network of multiple layers. So each weight is connected to each other weight, like this one, right? This is the type of neural network structure that you have. Now, what we want to achieve in regularization is that a small change in the input shouldn't affect the output of the neural network, right? That is the essence of regularization. And one way we can achieve that is it shouldn't be sensitive. The learning of the neural network shouldn't be sensitive to small perturbations in the input. And one way we can enforce that is by training the neural network by dropping out certain weights within the neural network. So the neural network becomes invariant to small changes within its own structure. So this idea was originated back in the 90s by something called it had a very cool name called optimal brain damage, but it led out to this idea called dropout. And the goal over here is that we want to randomly, during training only, what we want to do is we will drop out random weights that connect these. For example, we can drop out this weight connecting these two neurons, this neuron to this neuron, and we can drop out this one to this one, and then we can update the other weights as if these weights were not present there. And what that is going to force is that it's going to learn to be resistant to small perturbations in the input structure as well as the structure of the neural network itself. So this is what the effect of dropout is. You can implement dropout at any layer of the output neural networks using nn.dropout, and this is a paper back in 2014 which introduces dropout, a simple way to prevent neural networks from overfitting, because it certainly limits the structure of the neural network in training. So let's say if you got a fully connected neural network like this, what we'll be doing is that during training at a random, we'll be dropping out within each training cycle, we'll be dropping out these weights at random, and then we'll be training the rest of the neural network as if these weights were not present. So we randomly drop units, and what that allows us to do is at a given instance, your neural network can have a structure like this. At a different training instance, your neural network is going to have a slightly different structure. And you're at the end of all the training cycles, your neural network will now be resistant to small changes or perturbations within this structure, and that is going to it's going to be more regularized. It's essentially capacity or the learning complexity of your machine learning model, and that is a very easy way of achieving this. You just need to add this single line into your PyTorch code, and if you see this thing with written after a certain layer within your neural network, what this essentially is saying is that during training, drop 50% or zero point 0.5 out of 1 weights at random. So this is pretty high dropout that can essentially regularize your neural network. You can choose smaller values of 0.1 or 0.01 even. That is going to drop a smaller number of weights within your neural network to achieve this regularization effect. The other thing that before moving on, let's analyze the impact of doing dropout. So if you use a standard neural network from the MNIST dataset, for a given test dataset, you get an error rate of 1.6 that was done in 2003. If you use a support vector machine with a Gaussian kernel, it gives you an error rate of 1.4. If you use a neural network with dropout, you can actually get, and with some fine-tuning tricks, you can get pretty low errors within your neural network, even if your neural network is pretty large, like this particular neural network, which has 500 neurons in the first layer, 500 neurons in the second, followed by 2000 units. So this is a pretty deep and pretty big fully connected neural network. And you can add, you can have the same dropout structure after each layer to achieve this effect. Okay. The other thing that we want to understand is the effect of batch normalization that we had skipped over while we were going through this particular code, right? That we had discussed on how to implement neural networks or convolution neural networks in PyTorch. So it had this batch norm thing over here. Now notice this number 16. This simply matches the number of output channels that we have. So there is nothing more than that over here. Okay. So this is an operation that is performed to each of the outputs of your convolution neural network filters. Okay, so each of those feature maps is going to be batch normed. But what does it mean exactly? Or why do we want to do that? It's a means of enforcing regularization so that you end up with a machine learning model that generalizes to unseen test examples. So given a batch of examples of n examples, each dimension of the example is normalized to zero mean and unit variance. So it's essentially a way of doing standardization within the batch. So let me explain that. So let's say you've got a bunch of examples. Let's say you have got a batch size of 8. So you pick at one time 8 different examples that you pass through your filter and they produce their output. Now, what we want to do, or what batch norm does, why we do it, that's going to be a separate story. But first understand why, what it does exactly. So let's say you got outputs for each of those inputs, that is after convolution. Let's think of a single convolution block that you pass each of these images into, and then that generates these images at the output. Now these are going to be images, so you end up essentially with 8 images over here because you have a single filter and you had 8 different images that were passed in that particular batch. So I'm just going to think that there are 8 different images over here. What batch norm does is that it standardizes each of these images to have zero mean and unit variance for this whole batch. So first it computes the whole the input, a mean image and a variance image, and then it does standardization of that, much like we had talked about standardization earlier. And then it does it for each of those convolution outputs and carries on with this training. So this is the process what batch norm does. So it's essentially a way of doing the following. You take all the input images, you calculate the mean, you calculate the standard deviation, you normalize or you standardize your input. This small epsilon is added just because we don't want to end up with 0 in the denominator if your variance is going to be 0. And then what you do is you do this batch normalization step. Okay, so that's what this does. And we saw that sometimes standardization can be really useful. But in case of deep neural networks, what can happen is if your neural network, if the output of each correlation filter or convolution filter is not reduced to zero and doesn't have a mean of zero and a standardized variance within it, you can have pixels, you can have data that is pretty large, and that can generate very large outputs, uh, which would get you into that vanishing gradient or exploding gradient problem that we had talked about earlier. So this can be used as a way of reducing that effect. Now it's really important that you understand what's going on over here. For a given batch, we do standardization, and that standardization helps us with not producing, or it helps us generate standardized outputs, which now are resistant to these changes in the input distribution. So that is another way of achieving regularization in this case, and it can be more effective in comparison to dropout, and it eliminates the need of pre-training. This is an effect of the impact of this that was reported in the original paper that was proposing batch normalization. Even if you have a very deep neural network, it does a significant amount better than having dropout. So this, if you want to understand it in a bit more detail, I welcome you to go to this link where they compare dropout and batch normalization and see that if you use batch normalization, you don't require dropout, and you'll be able to do you'll be able to get much better generalization performance, even for very large neural networks. Okay, so that is the impact of this. If you think about it, this mean and standard deviation calculation is dependent upon the batch size that you use, right? Because if you use a very small batch, let's say smallest batch you can use is 1, then this is going to be a very bad estimate of your overall variance and your mean, right? So when you're using batch normalization, ensure that you have enough samples within your batch. Now there are more techniques or more sophisticated techniques that actually even do better than batch normalization, but most of these existing neural networks that are typically used in transfer learning protocols have this batch normalization built in. So if you look back now at the code that we had studied, this thing over here uses, there are going to be 16 batch normalization parameters. So each of that is going to be, it's called a batch norm layer, but it essentially what it does is that it computes the mean and standard deviation and saves those as parameters within your network for each output of your convolution neural network. And once you have it in training, these norms are updated as you go along through your training dataset. However, once you are done training, you don't want to update these any further. That's why it's really important to specify model.eval within PyTorch so that you don't update these batch normalization parameters that are there, and you don't want to update them with the gradients as well. So this is required if you have batch normalization within your architecture. So I hope now you'll have a better understanding of different types of regularization parameters that you can use. Remember, the goal of regularization is that we don't want an input to have an effect, a small change in the input to have a much larger effect. And that can be controlled by controlling the number of filters you use, the number of convolution blocks you use, the number of neurons in your fully connected layer as part of your convolution neural networks that are used, the filters that you use, the pooling types that you use. Each of them has a direct or indirect connection to regularization. You can use dropouts, you can use data augmentation, you can use early stopping, you can use norm constraints, you can use batch norms. So it's really important to understand, first of all, the concept of regularization and how these different things in a neural network that are we calling hyperparameter has an impact on regularization. There's some really interesting phenomena that we haven't talked about. One of them is called the double descent phenomena. So sometimes what can happen is if you're training your neural network and its loss is decreasing over the training data set, so we are getting convergence, What can happen as well is on the validation data set, we may see that your error starts rising, but then it starts falling again. And what we want to do is, and then it starts rising again. So we can have what is called a double descent. And there are people trying to figure out this as a problem and how early stopping should be used. But typically, it's okay to stop at the location where you have minimum error over the validation data set. Okay, so I hope now you have a better idea of how to do neural network training. So one of the things you can use, or when you're using a neural network, one of the things you can run into is that your neural network are not able to generalize. Revisit these slides and think of all of these factors and how these impact your particular problem and what should you be using to sort of as a debugging guideline when that happens. Okay, thank you.